All right. Hey, folks. Happy Tuesday. Hope everyone is having a good week. Going to be a shorter stream today. Um, I'll only have about an hour here, so hopefully we're able to get through a few different things. Um, and cool, it looks like video is coming through. If you have any trouble with video or audio, definitely let me know. Audio seems to have been sorted out on the past couple streams. The video has started freezing or has continued freezing for just the webcam, which isn't really that important as long as the screen comes through. But if you have any issues, feel free to drop them in the chat. Also, if you just want to introduce yourself and weigh in or jump in and provide comments on anything we're doing today, definitely feel free. The more participation, the better. But let's go ahead and jump into it since it's going to be a shorter stream today. And I am going to grab the right window here, and we'll keep that going and should be coming through here shortly. So today we are going to be looking at control transfer instructions. So past couple streams, we've been looking at RISC-V 64-bit integer instruction set instructions here. And actually, it looks like we haven't pushed up the latest here, but I'll go ahead and pull it up. So we've been documenting not only their structure, which is a bit of monotonous copy and paste, but also is helpful for committing to memory and talking through each of the instructions. But if we go over here, we can see that we're going through the RISU and then the B and J variants for the instruction formats for RISC-V. Like I said, we're using RV64I as the base for our instruction set here. Last time we were looking at some control transfer instructions, so that would be comparison and branch and jump and link. So we're looking at these B and J formats. So I think that we got part of the way through here. So we had the B format instructions. So it looks like we just did load store, and then we just got to B, and we didn't do any of the J instructions quite yet. So we can certainly get back to that. I have up here the unprivileged specification for RISC-V, which is what we've been going through. If you've been on any of the streams, you can see that. We're looking at control and transfer instructions. We're looking at RV32I, but because RISC-V has 32-bit instructions for all X lengths or register width, if you will, or I guess data width would be more accurate. Because it has, for all of the data widths, you're using 32-bit instructions. So these control and transfer instructions are the same between 32I and 64I, which is why we don't see any adjustments to control transfer here. So we were looking at the B-type instructions last time, I think. Yep, the conditional branches. So we noted a couple of those down. And I want to see where the J instructions. Yeah, so what we want to talk about today is pipelining. Sorry, not pipeline. Well, pipelining probably, and branch prediction, and specifically this note on return address stacks here, which is kind of an interesting thing to include, and talk about how J format instructions translate into, or how J format instructions help give hints for return address stack usage. Also, good to see you, Daniel. Thanks for joining as usual. Hope you had safe travels to and from the Open Source Firmware Conference. It was definitely cool to see some of the social posts from that. Very, very jealous. All right, let's jump back over here. Let's just go ahead and jump to the J format instructions. So they're going to be unconditional branching. So we'll just copy this down and J format. And we can actually get rid of these because we're going to be looking at something pretty different here. Okay, so unconditional jumps, right? So we were looking at conditional branches, and now we're going to look at unconditional jumps. unconditional, well, I guess we can say branching instructions. All right, and J format is, the J format is different than the B format, so we can see that here. We also use I-type instructions, which I don't think that we have. Okay, yeah, we have. So we'll also need to do some I format instructions up here. Oh, keep hitting that. All right, so indirect jump. Jump and link and indirect jump. Okay. So this is going to be indirect jump instructions. To do. And down here we're going to have we'll say not unconditional jumps, but jump and link instructions, which there's really just one. So use JType format where the J immediate encodes a signed offset and multiples of 2 bytes. The offset is signed, extended, and added to the address of the jump instruction to form the jump target address. We can probably just copy that over. Make sure this is all still working good. Looks like it. All right, cool. I'm going to workshop this a little bit. And the immediate is J immediate encodes a signed offset and multiples of 2 bytes. Offset is signed, extended, and added to the address of the jump instruction to form the jump target address. Offset 1 to 20. So we have a large offset here. Cool. So 20 byte offset, or 20 bit offset here. Be 20 bit immediate encodes a signed offset multiples of 2 bytes. The offset is signed, extended, and added to the address of the jump instruction to form the jump target address. All right, looks good. Jumps can therefore target a plus or minus 1 megabyte range. Jump and link stores the address of the instruction following the jump into register RD. The standard software calling convention uses X1 as the return address register and X5 as alternate link registered. All right, so we can note that down, that this is really the only instruction, so it doesn't fit super well with the other formats we were going with there. Also, I want to go down here and see if we can just see the jump and link. So yeah, we're not going to see any other J format instructions. So we have a dedicated one just for jump and link. Cool. And we talked about last time why the 4 kilobyte or 4 kilobyte could be targeted by the conditional branching instruction, I think it was. Yeah, right here. So basically because you had what was it in this case, 13 bits, with the lowest bit, the least significant bit, always 0 because we're using multiples of 2 bytes. The offset is signed extended and added to the address of the branch instruction to give the target address. So plus or minus 4 kilobytes. So in this case, we have 20 bits, and the least significant, right? That's why we're at 1 here. The 0th bit is going to be 0 always because we're in multiples of 2 bytes. And so if we take the address, then we can do the same calculation we did last time. So if we did 2 to the 20, or I guess, let's see, what was it? 2 to the 13, 2 to the 12, yeah. So 2 to the 20 is going to give us this, and 1, 2 bytes. Yeah, so let's actually do, so 1 megabyte, we can take this, right? 104.8576, 104.9. So if we take this and we swap these around, then we can see that if we have this many bytes, right, we have 1 megabyte. And since it's a signed offset, we can go plus or minus 1 megabyte in each direction. So that all makes sense. 20-bit immediate code sign offset multiple 2 byte. The offset is signed immediate. I'm just going to note down here. This is plus or minus 1. And up here we could probably say plus or minus 4 kilobytes. All right, looks good. And we need to correct the opcode here for JAL. One zero one 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 one. Okay, cool. As a reminder, two least significant bits of all of our opcodes are always 1 1, which we saw when we were looking at decoding. We can just use 5 bits, right? Because we always have the same for one of them. Let's see if we can pull that up here. Yeah, so I'm just using 5 bits for all the opcodes that we care about, because the lowest 2 bits are always the same. All right, change word. And control signals. We can go through our control signals here again, which we'll do momentarily. Let me close that. All right. We should also note down that jump and link stores the address of the instruction following the jump PC plus 4 under RD. C plus 4. So we're both unconditional and direct, right? We're specifying the exact address relative to the current program counter that we want to go to. Is there anything? Oh, yeah, we should go through the control signals. So for each, we've been going through and being explicit about each control signal. Oops. There we go. So here we should have branch is 1, right? High if instruction could result in branch. If high and the result of comparison is 1, then branch. Mem read, high if instruction specifies a memory address to read. We do not, so it's 0. Memory to register, high if the value to be written to RD comes from memory. Low if it comes from ALU operation. So last time we said that when we're not even reading from memory, then we just don't care about, or sorry, if we're not going to register write, then we don't care about mem to reg. But in this case, we are going to register write. So up here, we had the don't care because we had reg write is 0. So we actually do care here that mem to reg is 0. And we already know that register write, right, the destination RD, we are going to want to write to. ALU op codes operation that the ALU should perform or indicates that the funct field should be used to determine operation. Okay, so in this case, we don't want to use funct3, so we're not going to have 0, 1. Let me pull out the example we've been using here, which doesn't actually have jump. So we can just do this one for ourselves and see if we can get it right here. Let's see. ALU op. Oh yeah, also we have the mem to reg is inconsequential when reg write equals 0. Encodes operation that the ALU should perform. So in this case, we want to add, right? So do we have another case where we're adding that's not determined by funct3? So all of these stores have funct3. Yeah, pretty much everything we've done has been influenced by funct3. I think the one place we didn't, so the load instructions before storing it in RD. So we're not using funct3 to determine what we do in those cases. But in add and set less than, so all the immediate encodings, we are, I think. So ALU op here is 1, 0. And let's see if ALU op, yeah, is 1, 0 also for both the register ALU instructions as well as the ALU immediate instructions. So this is basically saying look at funct3 to determine. ALU op. So we have 0, 0, 0, 1 for conditional branching. So what are we saying with conditional branching, though? And does it mean, are we going to be saying the same thing? So the 12-bit immediate encode signed offsets and multiples of 2, and it, let me correct that. So I think we're going to have the same thing, right? Because I believe we're saying we want to add this, right? Where else do we use it? 0, 0. Adjust carry by adding the value of RS1 to the sign extended 12-bit offset. Instructions with U suffix are unsigned operations. Or maybe it doesn't matter. Maybe we aren't using the ALU op. Let me see if I can determine here. Oh, we need the... I guess we don't care, right? Because we determine whether to branch based on whether we get a... Actually, let me just diagram this out. I think it'll be more helpful. So let's pull up XCalDraw. So if we have the... Maybe, yeah, I'll just draw it. Okay. If we have the ALU here, we have 2 ports on it. So one is the result coming out here, which is going to be X length bits wide. And then the other one is whatever the comparison is. And if we have our control signals up here, control, and this is branch equals, we'll just say this is branch, and it's a 1-bit signal here, then we can use an AND here. Let's see if maybe I can draw one. Sort of. An AND, where we're saying if this is potentially a branch and comparison is 1, then our signal for whether to branch or not is coming out of this. So if branch equals 1 and comparison equals 1, then we're going to end up with the branch signal being 1, right? Otherwise, if we're not branching, we don't care about the output here because this is always going to be 0. And if we are, if it's a branch instruction but comparison does not equal, comparison is not true, right? So if it's break if equal and they're not equal, then we get 0 here and end up with a 0 coming out. Okay, so that makes sense. The other, so we essentially want this always to be 1 coming out of the ALU. If it's a jump and link instruction, so JL, then comparison is always 1. So I think that's should be a separate signal altogether. Or sorry, not a separate signal, a separate encoding. So right now, maybe we can work on encoding some of this. So we have 1 0, which is perform operation. Well, we're leaving out ALU control here. Let me see if I can find some more info. I know this is riveting television here, but this is somehow how it goes. Sometimes how it goes when you're working through some of these. So let's see. Okay, it actually has a yeah, it has a truth table that we can use here. ALU control lines. So the ALU op goes into the ALU control. Let's just kind of enumerate this here. So it goes through and gives us operations for the ALU control lines. So not the ALU op, it's what the ALU op is feeding into. So maybe to adjust this a little bit with a separate component down here that is ALU control, and it gets funct3 and part of funct7 coming in there, and then it also gets ALU op coming in, and then it tells the ALU what to do. And so ALU op is determined by opcode and determined by funct3 slash funct7. And then this is a combination here. All right, so basically what's coming out here, let's just call this ALU control. In the book, they're using 4 bits here. So what can we do in an ALU? We can add, we can subtract, we can and we can or. So we really only need 2 bits. So I'm not sure why. I'm not 100% sure why that we are using 4 bits to represent this. So it references the appendix here. So let's see if we can look it up. Okay, actually, so it actually uses Verilog here. But we have and or plus minus and then comparison. Okay, so add, subtract, and or less than, and then there's also a nor here. But if we have, once we get beyond 4, right, so we're going to need at least 3 bits to represent these. Still not sure why they're using 4. So it talks about set less than, which we can do with our less than instruction. All right, let's just match the control signals that they use for now. and we'll circle back to it. So for add, we'll note them down here. Let's see. We'll use we'll say the control signals for the ALU control, or I guess it's just the ALU. So control signals, 0, 0, 0 is going to be and and is fine. 0, 0, 1 is going to be or. 0, 0, 1, 0 is going to be add, and 0, 1, 1, 0 is going to be subtract. Okay. And then they give a truth table. See if I can get back to that. Okay, so the ALU op, we're just calculating from the op code like we already said. Should be add. So for ALU op, it actually enumerates them. Should be add zero, 1 is subtract and test if equal. And then 1, 0 should be use funct 3 / funct 7. All right, that looks good. Control signals. So in the case where 0, 0 or 0, 1 are always going to just translate directly. And then there's considerations for each of the funct 3 and funct 7 combinations. I don't think it talks about jumps anywhere in here. But we should be able to reason through it anyway. Okay. So let's get back down here to our jump instruction. we're doing the adding the 20-bit immediate to form the target address. We're doing that in a separate adder, if you will. Okay, so it has an example. So our ALU control is really just like don't care here. And we don't have an RS1 or RS2. But we want to say definitely branch. So select the adder. So here we want this to always be 1. So we need the comparison here. Yeah, so I'm curious about how we determine whether to. So if it's always going to result in a branch, we need the output from the ALU comparison to always equal 1. But we don't have RS1 or RS2 values. So potentially we could use a different ALU control to just say like that we want to, it's just true, like please branch here. There is an example of a JType in here. And with the so before we add the control, actually the branch logic here PC source. There is basically no instruction decoding happening here. The immediate gen goes into the adder. The PC does not require write control since it is written once at the end of every clock cycle. The branch control logic determines whether it is written with the incremented PC or the source target address. So it has a separate control signal at that point, but it's not. It's calling it PC source. But we basically just don't have the control signals yet. So, okay. Now that we have looked at the function of each of the control signals, we can look at how to set them. The control unit can set all but one of the control signals based solely on the opcode and funct fields of the instruction. The PC source control line is the exception. That control line should be asserted if the instruction is branch if equal, a decision that the control unit can make. And the zero output of the ALU which is used for the equality test is asserted. To generate the PC source signal, we will need to AND together a signal from the control unit, which we call branch, and the 0 signal out of the ALU. Figure 4.21. The 0 output of the ALU. I'm going to go back and take a peek at the ALU again. And okay, so looking at the 0 signal again, we will use 0 detection output of the ALU shortly to implement conditional branches. So in theory, could we just give it a signal that is always going to evaluate to, well, no, the sources are RS1 and RS2, which are going to be actually just immediate portions of the immediate field. Okay, so I'm seeing here that, so I think we can just use a different control signal here where we can say, so it's using 12 in this case. Or sorry, no, it's using, if it doesn't match one of the other signals, it's saying that, we just write 0 to ALU out. And so in that case, if we're doing the A is less than B results in 1, 0, so break if equal or break if not equal, etc., or break if greater than, break if less than, then we can just say that it's some other signal. But I don't know what the ALU op is. Subtract and test if equal. So maybe either 1, 0 or 1, 1. We'll put a question. Let's say 1, 1 and to do. And maybe we'll just say 1, 1 some say 1 1 is the branch signal, perhaps. That should work. Okay. Wow, we spent a lot of time on that. Sorry, folks. So basically what we're saying here is if we have the ALU out, so in the ALU, we're saying we're either going to, actually let me draw the inputs as well. So RS1 and RS2 here. RS2, and then the result is some operation based on these. So for example, if we wanted to say RS1 is less than RS2, if that was the comparison we were doing, then we could say true 1, false 0. And so if we said break if less than, so BLT, everyone's favorite instruction when they're hungry, so comparison would be 1, and we'd end up with 1. So if instead we just have a, let me change this to ALU out equals, we'll use Verilog syntax here. So we'll just say that 1 1 means ALU out equal or is 0. There might be a note in here that I just missed that's saying that more explicitly, but I think it just doesn't talk about jump instructions, which is fine. Whoops. And comparison is ALU out equals 0. So if it equals 0, then we're branching. If not, then we aren't. Okay, so in the case of break if less than, or I think the example, break if equal. So if RS1 is less than RS2, yeah, then we get 1. If they're equal, right, then this is false. But it's also false if the, oh wait, sorry. We use the subtract, and so we can do break if equal by subtracting RS1 minus RS2. So it's just a normal subtraction here, and then our comparison will be ALU out equals 0. So break if equal, if they're equal, then we get 0 here, which means our comparison ends up being a 1. Okay, perfect. So this one could be break if greater than, I don't know, I can't remember if RS1 or RS2 comes through. So probably break if greater than. What is the actual instruction? Break if equal, break if not equal, break if less than, break if greater than or equal. So in this case, if RS1 is greater than RS2 or they're equal, we're going to get a 0. So let's say this is BGE. This would be BEQ. And this one would be something like jump and link. Okay. Let's spend a few minutes, since that took me forever to do. And did we actually, yeah, we got that there. Let's spend a few minutes talking about the actual return address stacks. The jump and link relative, or jump and link register, sorry, instructions will generate an instruction address misaligned exception if the target address is not aligned to a 4-byte boundary. Instruction address misaligned exceptions are not possible on machines that support extensions with 16-bit aligned instructions, such as a compressed instruction set extension C. Return address prediction stacks are a common feature of high-performance instruction fetch units, but require accurate detection of instructions used for procedure calls and returns to be effective. Require accurate detection of instructions used for procedure calls and returns. Okay. For RISC-V, hints as to the instructions usage are encoded implicitly via the register numbers used. A jump and link instruction should push the return address onto a return address stack only when RD is X1 or X5. Jump and link register instruction should push pop a return address stack as shown in table 2.1. Okay. So when the register is either X1 or X5. Jump and link instruction should push the return address onto a return address stack only when RD is X1 or X5. Okay, so we only have one instruction to work with here. We'll note that down. Push onto return address stack when RD equals X1 or X5. Okay, so when, well, first let's just look at our registers here. I think we have them listed somewhere. Here we go. X1 return address. So if RD is a return address, that makes sense. Temporary alternate link register. Return address alternate link register. So let's maybe look up return address stacks to provide some context. I saw a good, here we go. I think this is this Georgia Tech one. We've seen branch prediction done for branch and jump instructions, but what about function return instructions? Functions are designed to be called anywhere, so the return address will not always be the same location in code. This makes them tougher to predict using our current methods of branch prediction. We might need to look back at those. How do we prevent from fetching instructions from the wrong location when returning from a function? The return address stack is a separate predictor used specifically for predicting returns. It operates similar to the process stack in that it pushes and pops return address for function calls onto the stack. Primary difference between a process stack and the return address stack is that the return address stack is a very small hardware structure designed to make a prediction very quickly. So what happens when the return address stack is full and we continue to call into more functions? We have two options. Don't push any more return pointers into this return address stack. Wrap around. Okay, yeah. So we can fill it up. Got it. So it's better to wrap around and overwrite. That's not really what we... As we acquire the next instruction, we decode a little bit to determine if it's a return instruction. So we're trying to give it hints, though, instead of having to do this. It'd be great if we had more time to go through and show an example of doing a function call. Actually, you know what? We might have one. Let's see if I have one on the blog here. RISC-V bytes. Oops. Do we have any jump and link instructions? Well, we're not going to see the decoding of it, though. But here we have T0 and RA. So let's take a peek at that. I believe that, where did we have our listing? Oh, here, okay, here we go. T0, right? Alternate link register and return address. So there we see actually that when we are, when it's a function call, which is the case for both of these here, jump and link, we've got T0, maybe I'll zoom in a little bit. So jump and link T0, and we're going to runtime more stack, which I talk about in this post. And here we're doing I lost it, jump and link runtime convert T64, and the return address is the register. So this would be X1, this would be X5. So in both those cases, we'd push the address onto the return address stack. Yeah, and once again here. So let me make sure I've kind of internalized that here. Oops. Went too far. We use implicit hinting tied to register numbers and the calling convention to reduce the encoding space used for these hints. Okay, so I think that's a really good point. Oh, also, it looks like I missed Daniel's comment earlier about shift operation. Sorry about that. So for jump and link, it's easy, right? If we're going to be coming back to this, if this is the return address or alternate link address or alternate link register, then we're going to need that later. So we put that on the return address prediction stacks. So that allows us, let me see if I can draw this up real quickly. So let's say that we have, some series of instructions that we're processing here. And we have our return address stack up here. So this just has entries in it. And so we do something like a jump and link RD and some immediate. And so we take the return address and we push it on the return address stack. So it's at the top. So we'll call this 0x1, 0x1. Okay, and then let's say we jump to this instruction here, and we have something like a break if equal here. So if we're going to continue executing instructions down both the, so this is a conditional branch. If we're going to continue executing instructions down each path, then we need to be able to know what the return address is. So it's conditional branch and return, I guess. Then we need to know where we're going to return without popping it back off the stack, I think is the, so if, let's say, conditional branch and this is a return. On the process stack, we also have the return address. We'd store the stack at the beginning in the function prologue. Let's see if we can find an example of that. Yeah, so we move the stack down and we store the return address on the stack, but we can't, well, here at the end, we load the return address back and then we return, but we can't load back into the return address. Right now, the return address, well, if we branch from here, right, we're going to overwrite the return address, for example. And so if we had something like a branch in here and then we got to return, the return address isn't in our stack right now. So we need to pull it off the return address stack. And I think I've got that correct here. But let me see if I can go back here. For branching, but what about function return instructions? Functions are designed to be called anywhere, so the return address will not always be the same location of code. This makes them tougher to predict using our current methods of branch prediction. Yeah, okay. So the return address is whatever the return address is for that current stack frame. So this would be the return address stack. And let's say this is the process stack. And then we also have our registers over here. So, okay, we do have the return address also here on the stack. But when we execute the return instruction, it's going to use whatever RA equals, which for this could be anything at this point, right? We push the return address onto the process stack, and then we might have loaded something else into the return address register. So just executing return is not going to work for us. But we can pull it off the return address stack to know to return to. Okay, so that's actually quite clever. Okay, so we were able to sneak that there, and at the end I went a little bit over here. Cool. As usual, a little messy here. Still trying to tighten up, moving through this stuff a little faster. But got a good sense of the ALU and when we're going to have to signal with it. I feel like, sorry, to be clear, when we are going to have to say just branch, right? So make the comparison equal to 1 so that when it gets into the AND that we do when we compare with branch from the processor control or the CPU control, as I was calling it, and the ALU output, that when we AND those together, that we do get 1, right? So we branch and we take the branch address. Cool. I'd also like to look up some examples of when return address or of instruction sets that use explicit hints in the return address stack. That would be interesting. Anyway, cool. Let me switch over. I think that my video kept working this whole time. Looks like it did. But I do have these bars on the side of it, which is kind of annoying. But anyway, thanks, folks, for coming out. As always, please feel free to let me know if I can do a better job of making these useful. I kind of take this as time to be working and showing that, and then try to put out the blog posts, which are a little more refined. But also would be interested in doing some more refined videos or live streams. Thanks to everyone for coming out. Feel free to reach out, as I said, and I hope everyone has a great rest of your week. I might stream again this week. Hopefully we'll also have a blog post or two. So have a great week, everyone.